So hello and welcome to our webinar on demystifying the 5G new radio physical layer. So Andreas and myself, we would like to discuss 5G new radio as specified in 3GPP release 15 recently in December last year. So we have also included in our webinar today a live demonstration using our instruments here, test instruments like a signal generator, SMW200NA, and a signal and spectrum analyzer, the FSW from Rohde and Schwarz. So let's start then. So we have structured our webinar today in two parts. I will do a very short introduction, and then we have the 3GPP standardization status, and also discuss the network architecture. And then the focus will really be on the physical layer details, including a focus on the non-standalone mode. So for the introduction part, very shortly, so 5G is really reality, or has become a reality. You probably noticed in the Winter Olympic Games that there have been first services offered by 5G. So we have here the example of a bus that is connected and takes a lot of data in there. And we have also services like virtual reality, where you see the Winter Olympic Games or the specific sport events here out of a sportsman, for instance. So you have seen these in the Winter Olympics that recently took place in Pyeongchang in South Korea. So this is, of course, new radio or pre-new radio, if you like, pre-5G. It's not the really based on the specification we are going to discuss today, but we all understand that these services are going to migrate to adopt the 3GPP new radio specifications that have been recently finalized. Okay, so let's dig into the first part, which is then the status in 3GPP, as well as the network architecture. So you have probably noticed this time plan in 3GPP. We have really reached the first milestone, which is the completion of the non-standalone mode specifications that has been achieved in December. Although we have to say there are a lot of corrections still ongoing, and also the ASN1, so the protocol specifications, are going to be completed in March this year. So in following that, we will also have completion of the standalone mode, and that is anticipated for mid of 2018, as you can see here. Overall, first commercial deployments are expected in 2020 or even earlier than that. We come to this at the very end of our webinar. Very shortly giving you an overview on what is this new technology about. You see these four pillars are maybe the main cornerstones of this new technology, which is including adoption of new spectrum, of course, the new high spectrum, which is maybe going as far as centimeter and millimeter wave range. You see these mentioned frequency ranges 26, 28, 39 gigahertz, which are of importance. We have the adoption of active antennas, massive MIMO and beamforming applications. We have the capability of connect LTE and 5G at the same time, so the multi-connectivity feature is included. And also we have this high flexibility or in the core network, adopting software-defined radio functions, virtualization functions, as well as a very high flexibility on the air interface. For this webinar, we really concentrate on the last two here. So discussing the non-standalone mode in combination with LTE, and also discussing the flexibility on the physical layer. So doing that, we discuss or explain shortly a little bit of a vocabulary, because we have now the existing expressions you are maybe aware of, like the LTE core, the EPC, which is having the mobility management entity function, and also the serving gateway, which is then doing control and data. You are maybe aware of that. Of course, also that the LTE base station is named eNode B. For 5G core now, we are talking about the next generation core, so NGC, and also the functions are slightly differently named. You have got an AMF, access and mobility management function, which is taking care of the control part. And we have a user plane function, which is the UPF for the data. And then we have a base station, which is now the G-Node B. And then we have to be careful then, because it is also the dual connectivity option, where both base stations are involved in the connection. And then one is taking the master role, and the other is taking the secondary role. So we talk about MN and SN nodes that might be either LTE or 5G, depending on what it is. So going now into the architecture options. So as I said, we will concentrate on the NSA mode. However, there is also the standalone mode, which is option 2 here at the right-hand side of my slide. And that is maybe advantages from, or has advantages from the UE implementation perspective. but it will be specified, as I said, or completed in terms of specifications by mid of this year. So we concentrate on NSA first because that is what is almost completed with ongoing corrections, as we said before. So for the option 3 here, which is named EN, E-ultra NR dual connectivity, it's important that we have the MME of the EPC exclusively communicating to the LTE base station, and it's concerned it's not concerned all with the 5G base station, right? So for the control plane, it's going over the LTE side, and the LTE side is also the master here. For the user plane, both nodes have S1U interfaces to the EPC core, and only one of these two is active at a time, so it's not simultaneous transmission here. And that brings us now to the details of this specific option, which I'd like to discuss on my next slide. So here you can see a detailed evaluation of the different option 3 sub-options, if you like. We talk about split bearers or secondary bearers, and we have the master MSG or the secondary SCG bearers here in focus. You see an interface between the both nodes, which is the XN interface. So for 3A, 3X, and 3, that means user data is transferred between the serving gateway of the LTE core network and the secondary G node B. The secondary node B forwards part of the user data over the X2 interface to the LTE base station. And this concept is understood as split bearer, as I mentioned. And it seems to be the favorite one, really, that the operators prefer in terms of real implementation in commercial networks. That's our understanding. The importance of the split bearer concept is that both nodes, master and secondary, are using their own schedulers and therefore decide how and when these data is transferred to the end user device. So we had the starting point here to explain the architecture, and we will now go on with the physical radio and explain the basics here. And I'd like to hand over for that to Andreas.
So you may wonder why we spend so much time on the network architecture, but as you will see, it is very much important when we're discussing the physical layer of 5G and R. Before we come to the details, let's look at the basics first. And this following overview slide is basically giving you a summary of the key parameters. So let's look into that. So first of all, the access scheme that's being utilized by 5G and R is OFDM, cyclic prefix-based OFDM. This time in downlink as well as in uplink. However, up to 40 gigahertz and for the enhanced mobile broadband use case, you can still use a DFT spread OFDM, which we know from LTE uplink also as single carrier FDMA. Carrier aggregation is an option where up to 16 carriers could be aggregated to utilize a total bandwidth of up to 1 gigahertz as it is specified for 3GPP release 50. Here you can also see now a various bandwidth that could be realized per component carrier. For the two frequency ranges that are being discussed in 3GPP release 15, first frequency range 1 from 0 to 24 gigahertz, and then frequency range 2 from 24 to 100 gigahertz. We have these different bandwidths per component carrier. Up to 24 gigahertz, you can have up to 100 megahertz per component carrier. And for the millimeter wave frequency ranges, you see here 50, 100, 200, or 400 megahertz per component carrier. We have different subcarrier spacings for these different frequency ranges. As you can see, this is basically needed due to the higher impact of phase noise, especially at centimeter and millimeter wave frequencies. So you can see here the different splits. We can have 15, 30, and 60 kilohertz subcarrier spacings for frequency range 1, and then 60 and 120 for the data part, but also 240 for the synchronization signal part, which we will discuss here a little later. The maximum number of subcarriers basically dictating the mandatory FFT size to create the OFDM signal is 4096 for the FFT, and so we're dealing with a maximum number of subcarriers of 3300. And then the modulation schemes is also nothing new, nothing fancy. Everything that we know from LTE days, which is QPSK, 16 QAM, 64 QAM, and 256 QAM. In uplink as well as in downlink, and in particular, and only if we're utilizing DFT spread OFDM, you can have also pi over 2 BPSK as an uplink modulation scheme. The radio frame length is still 10 milliseconds, as it is in 3G, as it is in LTE for backward compatibility reasons. And we have a subframe duration of 1 millisecond. Due to the different subcarrier spacing, we're dealing with different number of OFDM symbols within 1 millisecond. So we have a alignment of that at symbol boundaries at every 1 millisecond. The MIMO schemes that you can see here is also nothing that we haven't seen in LTE yet. So we have maximum of 2 code words mapped to a maximum of 8 special layers in the downlink and 4 special layers in the uplink. The duplex mode is kind of interesting. For the lower frequency range, we can utilize TDD, time division duplex, and frequency division duplex, where at the centimeter wave and millimeter wave frequencies, we're only using time division duplex TDD. So that brings me to the first details here, talking about OFDM-A as the waveform, as the access scheme that we're utilizing, and the flexible numerology with the different subcarrier spacings that we have discussed earlier on. You can see here table taken from the specification with an exponential scaling factor, so to speak. So you have basically 2 to the power of mu times a base frequency for subcarrier spacing, which is 15 kilohertz, which is the subcarrier spacing that we're utilizing in LTE. Interestingly, we're only dealing with normal cyclic prefix length here, except for the use case of 60 kilohertz subcarrier spacing, where we have also an extended one. And you see basically, it's basically an upscale of existing base LTE numerology. So if we're now taking a closer look to this organization with the cyclic prefix, it is important to note that we're dealing basically with slots now that don't have a time definition like we had it in LTE. A slot is built out of 14 OFDM symbols, and now due to the different subcarrier spacings, we have a different number of OFDM symbols in total within one subframe, that is 1 millisecond. As you can see here from the slide, basically we're dealing with the situation that the first OFDM symbol within that subframe has always a longer cyclic prefix than the remaining symbols in that subframe. And like I mentioned, we have a total different number of symbols within that subframe dependent on the subcarrier spacing. So let's take a look at 2 examples here. First of all, 15 kilohertz, which is very much LTE-like. You can now see that we have 14 symbols within that subframe shown here, where the first symbol has that longer cyclic prefix, which is indeed the cyclic prefix length that we know from LTE with 5.2 microseconds. And then this is new, and this is different to LTE, all remaining 13 symbols now having that same cyclic prefix with 4.7 microseconds as shown here on the slide. In comparison, let's take a look at 60 kilohertz. So now we're dealing here with a total of 56 OFDM symbols, but again, the first OFDM symbol has a longer cyclic prefix than the remaining 55 ones. So this is the first set of basic 5GNR parameters for the physical layer. Before we continue on now and talking about physical channels and physical signals that are important, we need to understand how a 5GNR capable device would connect to the network. So let's dig into that. So what you basically see here now is our master eNode B that Mike already explained when we talked about the network architecture. And this is an LTE signal at sub 6 gigahertz frequencies, for example. And this LTE base station taking on the master node function here is basically broadcasting its capabilities that it can also use dual connectivity to connect a 5GNR carrier. This information is basically broadcasted in the system information block type 2. So any device that will connect to this particular base station, any LTE capable device would read in the system information block type 2, of course would ignore that information element that this base station is also ENDC capable, but a LTE 5GNR device would care about that and use this information basically during the registration process that you can see here now on that slide, during the UE capability transfer, that it also provides the information on 5GNR that's also supported by this particular device, which you see here on the right-hand side. All these different information, yes, I can also do ENDC connection. The 5GNR frequency bands and so forth will be transferred to the device. And so at that point, both device and network will know that they are 5G and are capable. So the next step is then basically doing the due diligence. As you can see here on that particular slide, basically the base station is instructing these 5G and R capable device of doing certain signal quality measurements on surrounding 5G and R carriers. These frequency range can be basically in the sub-6 gigahertz or millimeter wave, centimeter wave frequency range. So the question is basically, let's see what's around. And over the established LTE connection, the master inode B, the LTE base station, will send an RSC message as a measurement object NR. And here you're seeing the details on that measurement object NR being displayed, which is basically which carrier frequencies to use at, and certain other important information like the configuration of the so-called synchronization signal blocks. Why is that important? Because these signal quality measurements are carried out on the secondary synchronization signal, which is part of the synchronization signal block. So the question is, where do we find this particular signal? And that brings us to the first important 5G and R physical layer information. How do synchronization signal blocks work, how they are organized? And that's what we're looking at right now. So basically, 5G and R adopts the concept of synchronization signal blocks for the initial synchronization. Such an SSB consists out of a primary and a secondary synchronization signal and the physical broadcast channel. So from that point of view, it's not much different than what we have in LTE, how we achieve their initial synchronization. However, these signals, these sequences are different, and how much bandwidth they are occupying, how often they are being transmitted from a time domain perspective, where they are in the frequency domain perspective. All these are different from what we know from LTE, so it's worthwhile to take a look. So first of all, let's understand how much bandwidth is occupied. You see that here in the graph. We basically have 20 resource blocks being occupied in the frequency domain. Now with the different subcarrier spacings that I mentioned earlier on, of course, this is a different bandwidth that's been occupied based on that subcarrier spacings. You basically see here in the time domain 4 of the M symbols are occupied, and you're seeing this mapping principles here that we have basically the primary synchronization signal followed by the physical broadcast channel, and then the secondary synchronization signals basically occupied, surrounded by parts of the broadcast channel, and then the last symbol is also the physical broadcast channel. Due to the fact that we occupy here different bandwidth, the PBCH has to use a demodulation reference signals. This is due to the fact, which is also a difference to LTE, that 5G and R doesn't know or doesn't use cell-specific reference signals like what we have in LTE. So also important to note, or good to know, is that the number of cell IDs that are possible has been significantly increased. It has in fact doubled compared to LTE. The default subcarrier spacings that's being used for these synchronization signal blocks is basically frequency band dependent and will be initially specified by RAN 4 working group in 3GPP. And I mentioned the signal quality measurements that the device has to do are basically carried out as an RSRP, RSRQ measurement on the secondary synchronization signal, then the signal to noise ratio, and last not least, the transmit power and the details. I would like to refer you to the physical layer procedure specification, measurement specification 38.2.15 as part of release 50. So all these details brings us now to our first demonstration that I would like to show you right now. For that, I will use the vector signal generator, the SMW200A, as well as the signal and spectrum analyzer, the FSW. Okay, I'm right now here remote desktop into the SMW. You basically see here, I already picked the frequency range of one of the favorite 5G and R bands, and possibly the first deployment for 5G and R will be realized on the 3.5 gigahertz band. So I picked 3.5 gigahertz here as the frequency. What I have to do now is basically go into the baseband functionality, pick the 5G and R option, and once I loaded that, you see here basically a number of configuration possibilities. What I would like to do right now is only creating synchronization signals. So I have to go into the block node here, which basically means I'm configuring the framework and physical layer parameters for the base station. You see here the cell ID, so I can choose, for instance, 200 as a cell ID here. I can pick a particular channel bandwidth, which I already explained on our slide deck. So I'm choosing here 100 megahertz. And like I said, I have 3.5 gigahertz, so I'm using this exact deployment frequency range. Why is that important? That basically dictates how many synchronization signal blocks are transmitted in time. This is a frequency-dependent, carrier frequency-dependent parameter. So in that frequency range that I selected, 3 to 6 gigahertz, which is part of the specification or defined in the specification, we would have a total number of 8 synchronization signal blocks being transmitted in 5G NR. So the next step would then be, of course, to configure these secondary synchronization blocks. Basically, what I explained during the slide deck, basically we need to pick a frequency subcarrier spacing here. As you can tell from the frequency range that I picked, basically it's only 30 kilohertz possible from a standards point of view. Then, like I said, very flexibly to be transmitted from a frequency domain perspective, I basically can now place it anywhere within that bandwidth, where in LTE it was always being transmitted around the carrier frequency. So I can choose here, for example, an offset of 10 resource blocks if I like. And then you basically have a certain scenario, a mapping scenario that is related to the chosen subcarrier spacings. And something why we picked here 30 kilohertz in the example is because this particular subcarrier spacing has 2 mapping principles, and we will look at that during this demonstration. So let's start with the mapping principle case B first. So that's all I wanted to configure here on the generator, and now I'm just basically switching that on. The signal is being calculated, and now I can take a look at the FSW signal and spectrum analyzer and perform my RF measurements at this particular signal configuration. So as you can see here, I'm now remote desktop into the signal and spectrum analyzer, the FSW. So I have to call up the 5G NR personality here, which I'm doing over mode, and then selecting 5G NR. So once that is loaded, the very first thing that I will do is like setting the correct frequency, which is 3.5 gigahertz, like we had it on the SMW. And then I basically already see here in the power spectrum my signal, but of course I'm not yet synchronizing to it. So I'm doing basically measurement configuration, go into signal description, and basically now have to just choose the right frequency deployment range here. And then basically only have to go into the configuration. I don't have a bandwidth part. We will talk about that in a moment. And the last thing I do then is basically going into the synchronization part here and choosing my offset. And if you remember that, we had 10 resource blocks offset. And I was doing the case B in this scenario. And now we can already see here the signal. But of course, I need to do finding the right reference level that I want to measure here. So I can do that over AutoSet. We have that auto EVM functionality where my analyzer will basically go and find the sweet spot for this setting here, for this measurement. And I want to allocate here a few more measurements that we will talk about. So an allocation summary and an EVM over symbol measurement. So to fill that up here. And now basically we are analyzing my signal. You see here the synchronization signal blocks where they are transmitted from a power spectrum point of view. We also see the allocation table here, and we're seeing this allocation summary. And we see what particular modulation schemes are being used for these signals. So if I go into this constellation diagram, you basically see now the QPSK modulation, which is the physical broadcast channel. And then you see a BPSK modulation, which is basically the primary synchronization signal, as well as the secondary synchronization signal, which is fundamentally different from what we have in LTE. In LTE, the PSS is a Kazakh sequence, and we had that unity circle in the constellation diagram. So this is gone now. This is a change compared to LTE. The one thing that I wanted to show you in addition is basically here the allocation summary. We have the frequency domain being here on the y-axis and the time domain, so the number of symbols basically being on the x-axis. So we can basically zoom in here real quick and see that, like I mentioned, for that frequency range, we have these 8 synchronization signal blocks being transmitted. And this is the mapping case B. So I want to put your attention here basically onto these 2 blocks, which are transmitted contiguously from a time domain perspective. And the one thing that I want to show you next here is basically now when we're switching to the mapping case C, what changes, how this mapping principle changes. So let's go back to the signal generator and just choose case C for this particular example. So basically at the SIGGEN, I'm going back into that configuration where I can define synchronization signal blocks. I go into this scenario case B, and I just choosing C here as the example. Very simple. Now let's go back to the analyzer and see what happens. So as you see, we are back here on the analyzer. I'm just choosing case C here in the example. And if we now go back into the allocation, I hope you notice that now we have between the synchronization signal blocks a gap. This gap is actually 2 symbols. And this mapping pattern has been basically defined to enable one of the application scenarios that 5G is targeting, which is beside enhanced mobile broadband, which is the initial priority, ultra-reliable, low-latency communications. So these actual 2 symbols as a gap that we see here on the screen are basically meant for any latency-sensitive applications to have a chance to switch from downlink to uplink and send, for instance, an acknowledgement or non-acknowledgement back to the network. So you see here all this flexibility in 5GNR. And with that, I would like to switch back to our slide deck and hand it back to Mike for some further information on the 5GNR physical layer.
All right, so we are back now on our slides here, and what you can see now, the first synchronization has been done. And then, of course, the measurement of the UE has to take place. So what is the strength of the signals that I see on these different SSB H blocks that Andreas had just explained to us? So these measurement reports are provided by the UE to the network. And then the node B is initiating a secondary node B addition request via the X2 interface. So that is now setting up a secondary link. And that will be followed by a radio resource connection reconfiguration message with all the details you can see here on the left-hand side below the base station with all the parameters that are needed. And obviously, this is then also acknowledged by the end user device with a complete message. And after that, the random access procedure can actually start on the 5G side now, on the G node B, to add now the different communication links for our data transmission. So let's come to this. For the random access itself, of course, it is similar than in LTE. You have to know about the RATCH configuration you are able to use. So different preamble set, different preamble formats are defined. Details are on the specifications. We skip that. But the most important information is that you get that from a certain SIP information field that is pointed to from the master information block, right? So in this SIP1, you have the capability to decode the SIP1 configuration or information is coming from the MIP with all the details you can see here. So, and then we have a message exchange from the UE to the base station back, as you can see in the slide. There are not all details specified yet. We mentioned that there are holes in specifications. There is ongoing work in 3GP in terms of filling all these holes. One example is that the SIP1 content is not fixed yet, as noted here on my slide. But now, really, for the beamforming character in the new radio system, which is so important to our understanding, and we mentioned the occasions of these different synchronization blocks appearing in a frame. You can see here the case A example, which corresponds to 15 kilohertz subcarrier spacing, with a maximum possible 8 opportunities for these blocks being scheduled in that 10 millisecond frame. And then you can imagine that each of these blocks can be sent via a different beam. Yes, this is illustrated by the slide here, and all these different blocks have then also an index, which is ranging from 0 to 7 in this case. And this is, the number 8 here is corresponding to the frequency range between 3 and 6 gigahertz. It would be only 4 maximum possibilities when it's below 3 gigahertz. So you see, you notice already there are different cases for different frequency ranges we support in new radio. And in total, we have 5 cases, case A, B, C, D, and E. We have a total of maximum 8 opportunities for the lower frequencies, below 6. We have as much as 64 from these blocks being possible to be scheduled for the higher frequencies, so above 6 gigahertz. All right. So we have a minimum system information that informs the UE about the association of these different blocks to different beams. And that's something I also like to discuss a little bit more in detail. Obviously, not all these beams are reported. Only those beams with a certain strength need to be feedback. And also this threshold for this reporting towards the network is configurable by the network. So according to certain limits, it will be done only. Now on the details for this relation between the SSB blocks and the RUDGE preamble that is used by the UE, you have this information element displayed on this slide here. We have a RUDGE config common information element, and the zoom into this information element, you see a certain relation between the SSB ID number, that block that is used, and then the preamble the UE has to use in responding to the network because it saw this block now being the strongest. So the trick is here that the UE responds to the network with a preamble that indicates which is the best beam it was seeing out of these beam configured on these SSB blocks. And that, of course, can then be used to make scheduling of UE demolition reference symbols for beam forming in that data allocation for that UE. Then next, the data communication will start off with. So see now we have synchronized, we have indicated already in the very first attempt to the network which is the strongest beam, and we are able to communicate within base station. And from there on, we will have control and data configuration running. And this is again explained by Andreas now.
Okay, so Mike explained right now already how the synchronization works, that we have to read in system information. And that principle is basically very much the same as we have it in LTE. You need to read the control channel, you need to scan the control channel for a certain identity, the system information identity. You need to identify the resources, you need to decode the control channel, the downlink control information basically, and then check on the data channel where to find these resource block carrying that data, which is in that sense system information. That's the same for system information, paging, data. So let's dive into the control channel. Let's take a look. Some quick facts here about it. So first of all, we don't have a control format indicator channel anymore in 5GNR. I think I mentioned 5GNR does not use cell-specific reference signal at all. So also the physical downlink control channel in 5GNR will use a demodulation reference signals. And new to that is that the PDCCH is organized in so-called control resource set. We basically see here still modulation to be QPSK. The channel coding is polar coding, where for the data channel it will be LDPC coding, at least for EMBB. For ultra-reliable low-latency communications, that's still being discussed within the standards. I think I mentioned that PDCCH carries the downlink control information format, and a UE can monitor multiple core sets. So what you see on the right-hand side is basically now the organization of those core sets as control channel elements with certain resource element groups, where one resource element groups basically corresponds to one physical resource block. And you see here in an organization that the control channel can at most occupy 3 symbols in the time domain. The example shows here 2. And basically I zoom into one of these resource element groups, and you can see the 12 subcarriers and where the DMRS are mapped to. Interestingly, also there's an interleaved and a non-interleaved mode. And one thing that I wanted to show you on the slide is here that, like Mike mentioned, there are still like open items in the specification. In particular, for instance, at this point in time, the mapping principle is still being discussed. What do I mean by the mapping principle? Is basically how we filling this with data. So it's basically, I can do it either, for instance, first filling all the symbols and then subcarriers and then going into the symbol, or I can do something like this all the time. This is really something that's being discussed in standards right now, and soon should be finalized and decided. So beside the control channel, we have the data channel. Also, the data channel uses a demodulation reference signals, as you can see here, as a very flexible, powerful mapping of these demodulation reference signals, how many symbols are being occupied. And like you can see here on the slide, I took the freedom to take this information from our signal and spectrum analyzer, the FSW, where you basically see the different configuration types here, which symbols to start at, how the length is, so how many symbols are occupied, and if there is an additional symbol throughout that slot that's being carrying demodulation reference signals. So with that, one more important thing on the PDSCH, which is basically so-called carrier bandwidth parts. Now, what we have to understand on carrier bandwidth parts is basically you're having a channel bandwidth, let's say 100 megahertz carrier, and now you basically chop up that 100 megahertz carrier into certain bandwidth parts, and each of these bandwidth parts can now utilize one of the numerologies that we discussed throughout this webinar, so either 15 kilohertz subcarrier spacing, 30 kilohertz subcarrier spacing, 60 kilohertz subcarrier spacing, again, all depending on the deployment frequency range. And if we take a look how this can be organized, basically over time, this can change. You see here in the example, a bandwidth part 1, which is occupying 40 megahertz using 50 kilohertz subcarrier spacing. You see a bandwidth part 2. And the interesting part is now that we have an asymmetric bandwidth allocation that my base station, like I said, spits out these 100 megahertz channel bandwidth, but now the UE can basically have a much smaller bandwidth, looking only at 40 megahertz or looking only at even 10 megahertz. So you can change our front-end settings, switch filters, and go to a lower mode and power consumption as an example. But most importantly, these bandwidth parts are being designed to carry these different application scenarios. For instance, enhanced mobile broadband could be mapped to a bandwidth part that is utilizing 30 kilohertz subcarrier spacing, where a low latency application or ultra reliable application could utilize now a bandwidth part with less bandwidth, but that uses 60 kilohertz of subcarrier spacing. So as we told you throughout this webinar, a very flexible physical layer, very flexible air interface. Indeed, a lot of impacts from higher layers to configure that physical layer. One thing that we would like to show you now is, of course, a full-scale signal with different bandwidth parts, with different modulation, with different subcarrier spacings. And for that, we have to switch back to the equipment. And we're going to start with the SMW. So back here on the SMW 200A vector signal generator, I basically choose baseband again, 5GNR option, going into the node, choosing cell ID 0 as an example, but let's choose a deployment bandwidth of, for instance, 40 megahertz, and a deployment frequency range of 3 to 6 gigahertz, because we want to stick to the very interesting 3.5 gigahertz band here. Synchronization signal blocks real quick. 30 kilohertz again. Let's choose an offset. I had it before of 10 resource blocks as an example. Let's use the scenario C here. And that's basically all that I need to do on the node side. And like I mentioned, we want to use bandwidth parts. So for that, I have to choose the new block, users and bandwidth parts here. We do have the possibility to define now multiple bandwidth parts. So let's keep it simple for this initial demo. Choosing 30 kilohertz as my subcarrier spacing with 106 resource blocks as the total bandwidth. And that's all the settings I need to do here at the SMW, basically switching that signal on. And now I hand it over to Mike for configuring our signal and spectrum analyzer.
So we are back on the FSW side. So we go again into our new radio option. We have to set the frequency first, which is 3.5 gigahertz. And then I'm going into my signal configuration and check the deployment scenario between 3 and 6, our new set bandwidth, which is 40 megahertz now. And then let's check the synchronization. Oh, the auto detector already saw that we are in case C, and we have the right offset. Checking the bandwidth part, a single bandwidth part with a 30 kilohertz, resource block of 106 corresponding to the 40 megahertz. And then now for the scheduling, hey, what data did you use? We used only one allocation, I guess.
Yeah, Mike, one allocation, entire resource blocks for one user, and 64 QAM modulation.
So let's use the 64 QAM then here. Okay, the number of symbols is 14 in total. And also we don't have an offset, so we use 0. And plug that in. So I should be done. So look to the constellation. Yeah, that looks good already. Again, for finding the sweet spot, we use the auto EVM function here, setting the best levels. You see the auto level is ongoing. And we now have a full capturing of our signal in terms of capturing buffer. Also the allocation, again, is including our synchronization blocks at the right place. All other is data, 64 QAM. So you see with a little bit of configuration, of course, you have a very performant measurement of our signal that we generate.
So Mike, I think we have shown that 5GNR is a very flexible interface, lots of configuration possibilities. Yeah, so I think once the specification is done in terms of test and measurement, there will be most likely fixed signal configurations. We call them in LTE test models. So Rohde and Schwarz has decided on a few test models already, and that is just loading a certain signal configuration on a signal generator that matches later on the analyzer. So I will configure the signal generator real quick for that, and then Mike is talking about the signal analyzer again. So let's switch quickly to the SIGGEN. So we're going back into the baseband functionality here. The trained eye has already noticed that we have that test model block here. We just choose that. Right now there's 4 signal configurations. We talked about bandwidth parts. We just configured one bandwidth part in the recent example. So let's do 2. Let's choose the test model here with 2 bandwidth parts, 120 and 60 kilohertz subcarrier spacing per bandwidth part, and then 2 different modulation schemes. So I'm basically picking that, doing select, and firing up that signal here. Importantly to note, 120 and 60 kilohertz subcarrier spacing only applicable to millimeter wave frequencies. So I need to go from 3.5 gigahertz, which we use for this demonstration, to 28. And that's all I basically have to do. And now let's see how we can configure the signal analyzer. Mike?
On the FSW, I quickly set the frequency, 28 gigahertz, as we need it here. And then I go in my signal description, load the configuration file we have prepared for this allocation. And with that, I'm already done. Obviously, I can again do my auto settings here in terms of auto EVM, getting reference levels right and stuff like this. But with that, you are already set without going all through the submenus as we have been doing before. So obviously, as 3GP is defining all the 3GP models, test models, we will include them on top of what you have seen today. And with that, I guess we are through our demonstration part, and we will move over to the summary now. So in summary, we expect 5G new radio commercial networks deployments as early as 2019, 2020. We have seen that this network slicing in combination with the flexible numerology on our physical layer is really enabling these different services we are going to anticipate with 5G. And obviously the physical layer and its flexibility requires that we have not only high performance, but also easy to use test instrumentation for it, as we have been demonstrating today. We are very committed to support our customers with our test solutions as we did in the part. And we are working with all the industry partners here through the whole development cycle of defining, standardizing, and also implementing these products. And with that, we'd like to close our webinar today, and we hope that we demystified the 5G new radio for you a little bit more.
Thank you so much for your attention. I would like to close with an African proverb. If you want to go fast, go alone. If you want to go far, go together. Go with Rohde and Schwarz. Thank you.